Alright, thanks for watching, and today I would like to do a really nice exercise in dual spaces so you can check if you actually understand dual spaces. Namely, suppose we have a linear transformation T from V to W. Then what I want to show is that T is onto if and only if its transpose is 1 to 1. And actually here we don't even need to assume that V and W are finite dimensional. So this is always true, and then I'll also talk about the other direction you might think later. But how do we show this? Well, it turns out it's easier to show the negation. So P equivalent to Q is the same thing as not P equivalent to not Q. So let's show if T is not onto, then T transpose is not 1 to 1. And I like to remind you what T transpose is. T transpose goes from it's switched, so it goes from the dual of W to the dual of V. It takes a functional in W, that's an input, and spits out a functional in V. And simply G of T of X, simply by switching. Okay, so now suppose T is not onto. So if T is not onto, then the range of T is not all of W. So T of V is not all of W. And in fact, let W prime equals T of V, which again, it's a strict subspace of W. And here's the nice thing. Because we have a strict subspace, it turns out we can define a functional that is 0 on W prime, but that is not the 0 functional. So in terms of pictures, this is W prime, this is W. We can actually find a functional, let's call G star, or I guess G. That is 0 on W prime, but not 0 everywhere. And this is where we needed the strictness of the subspace. So because W prime is a strict subspace, of W, we can find G in W star such that, again, G is not the 0 functional, but G equals 0 on W prime. And in case you want to see the proof, at least in the finite dimensional case, all you do is simply you let W1 up to WK be a basis for W prime, extend it to a basis WK plus 1 up to, I don't know, Wn of W, and then you just define G such that G of W1 is 0, G of WK is 0, and simply G of, let's say, WK plus 1, it's 1, and then the other ones, whatever you want. Whatever. Because basically G will be 0 on W prime because it's 0 on those basis vectors, and it can't be the 0 functional because it's 1 on the WK plus 1 first vector. And I think something similar also works for infinite dimensional spaces because it is true for infinite dimensional spaces. You can take any linearly independent set and extend it to a basis. All right, good. So we have a non-zero functional such that G equals 0 on W prime, and I'm claiming this G makes T transpose not 1 to 1. In other words, with this G, we have T transpose G equals 0. So then, let's see. T transpose G of X equals g of t of x. But look, and again, that's for all x in V. But t of x, it's an output of t, so it is in TV, which is w prime. So in particular, we know that g is 0 on w prime. So in particular, g of t of x, it's 0. You see, because t of x is just some vector here in w prime, and we know g is 0 there. So in particular, t transpose of g of x equals 0. So t transpose g, because x is arbitrary, t transpose g is just a 0 functional. So in other words, this g, it's in the null space of t transpose. But remember, g was not the 0 functional. So we have a non-zero functional in the null space. So in particular, t transpose is not 1-to-1. Because 1-to-1 means the null space is trivial, but it's not. That's why it's not 1-to-1. So it gets messy, but now let's do the other part. So suppose now t transpose is not 1-to-1. Let's show that t is not onto. So suppose t transpose is not 1-to-1. Show t is not onto. Well, t transpose not 1-to-1, it really means this thing. It means we know that t transpose g is the 0 functional for some g non-zero. So some function, non-zero function in W, we know that t transpose of g is 0. So in particular, t transpose g of x equals 0 for all x. And by definition, this means g of t of x equals 0 for all x. But look, now if you want, suppose t is onto. And suppose y is in W. Then y equals to t of x for some x. But then, let's calculate g of y. G of y, in that case, is g of t of x. But we know g of t of x is always 0. So this implies g of y equals 0 for all y. But this just means g is the 0 functional. But remember, we assume g is not the 0 functional. And that's a contradiction. And this is why t must not be onto if t transpose is not 1-to-1. And this concludes at least the proof of this claim. So what we have shown is that, again, t transpose 1-to-1 if and only, t is onto if and only if. If and only if t transpose 1-to-1. All right, and in fact, it's also true that t transpose is onto if and only if t is 1-to-1, but you have to be slightly careful. So it is okay to replace t by t transpose. So what you get also is that just applying the same thing, we get t transpose onto if and only if t transpose transpose is 1-to-1, And that's the same thing as saying T transpose transpose is 1 to 1. But be super careful. This does not imply that T is 1 to 1. Because T transpose transpose is not equal T. But, I don't know if you've seen another video, at least now for finite dimensions, in another video we know that V double star is kind of like V with this x hat transformation. So really, if you think of an element in V double star as being of the form x hat, so this is V star, V double star. If you think of every element in V double star as x hat, then with that identification, T transpose transpose does become T. Because basically, what does T transpose transpose mean? It takes x hat as an input, I guess, in V star star, and it spits out T of x hat. But in particular, all those hat things, they are, all those hat things, they're isomorphisms. So really, if you forget about the hats, it is true that T is 1 to 1. So, in fact, let's show this. So let's show T transpose transpose 1 to 1, if and only if T is 1 to 1. But, so in particular, let's show T transpose transpose not 1 to 1, if and only if T is not 1 to 1. Okay, well, suppose T transpose transpose is not 1 to 1, so T transpose transpose of x hat is not equal 0 for some x hat not equal 0. But the only way x hat cannot be 0 is if x is not 0. And in particular, what do we know? This means T of x hat is not equal 0. And the only way this can happen is if T of x is not 0. Because here hat is also an isomorphism. So what we get, x not equal 0 is equivalent to T of x not equal 0. So in particular, this means T not 1 to 1. And this is equivalent to T transpose transpose, not 1 to 1. So at least in this, with this identification, it is true that T transpose transpose not 1 to 1 is equivalent to T not 1 to 1. And maybe there's an infinite dimensional way of doing this, but I think this is the nicest way. Alright, I hope you like this little dual space exercise. If you want to see more math, please make sure to subscribe to my channel. Thank you very much.